So I'm going to talk about the future is direct. And you might be wondering, what this picture of a bridge is doing about talking about DC. And, it's a perfectly good 100 years old bridge. It's functioning. There's even a car on it. But now imagine that somebody tells you that you're going to vastly increase the traffic on this bridge. I mean, you're going to have a problem. And that's exactly what's happening to our grid today. So, how are we going to deal with that? So my key messages to you today is that the grid of yesterday cannot power the world of today or tomorrow unless we do something significant. Also, that renewables, and Jim was alluding to that, including microgrids and DC power, can be a fast solution to help meet today's need of energy. And also that microgrids and nanogrids can help to meet the demand where it happens. And then I have a couple of case studies which I hope will illustrate the point. So the reality today is that our grid is aging and demand is rising. And you see some of these numbers. These are US numbers. 70 power of transmission systems are 25 years old. Average life of transformer is 40 years. And average life of protection gear is about 25 years. Now, we have incredibly fast rising demand, and it's about 3 to 5% a year, which is caused by the data centers, by the EV charging hubs, heat pumps, factories, and telecommunication, particularly in factories, robotics. So what does it lead to? It leads to outages, and all the outages in Texas and so on. This is not just USA. This report by the Electricity Canada is actually painting the same picture: aging grid and congestion. Now, as Jim was alluding to, how to meet this demand takes a long time. The nuclear power station take about 7 to 12 years. The SMRs supposedly going to take 3 to 5 years. They have not been built yet, so we'll see how that goes. As our other speakers were saying, the business needs the actual energy now. Small businesses need it within 1 year. Data center needs it within 2 years. So there is a big gap between the way we can supply the energy and the way it's needed. Now, the cost is also another factor. It's going to be great to have the nuclear, in the future. It's going to create some jobs, but it's costly. And when you compare it to renewables, when you compare it to solar and storage, wind, and also when you see the job numbers, we need the jobs now. And we have a double the amount of jobs we can get from the nuclear energy. So we've been prouding ourselves, what a great grid we have in Ontario. And we did, in about 2020, we had a very low emissions, but now it's rising. And, we just got that fossil award in Bethlehem at COP 2030. So, we're not doing that well. If we're going to have the heat pumps and if we're going to have EVs and it's going to be powered by the fuel, by the fossil fuel, then those emissions not going to go down. And, we can certainly see the demand and the peaks rising. So we do have a plan, which is great. There is now the Ontario Integrated Plan for the power and the strongest economy in G7. And it does have some renewables in it, which is great. But it's not nimble enough. I mean, when you actually sort of look at, if you read the plan, there is not anything specific in it how this is going to happen. And while the Energy Board is talking about some distributed control operators, and they talk about sort of mud wires solutions, that's still not very well worked out. So, I mean, we do have a problem with renewables, partly because the grid has not been built to take them. It was never designed for solar panels, for digital devices, and for electrified transportation. And admittedly, the renewables do create local grid congestions. The local distribution companies actually don't have mechanism to verify and pay for that kind of a distributed flexibility, and therefore the distributed energy resources are remaining stranded behind the meter. And their response to demand is very coarse, slow, and inefficient. So there is a problem. So, could DC power system, things like grid-connected infrastructure, allow us to direct use, storage, and distribution of DC power, which would then cut down on energy losses, reduce conversion cost, and improve the whole system efficiency? But this does not have to be done overnight. It can start with smart modular integration. So what we really need is decentralized energy ecosystem. So we need to have this kind of a bidirectional connection, backwards and forwards, between the renewables, between the local distribution grid, between the storage, and between the users, which could be the DC microgrid. But what do we really need? There's got to be an exchange, and we call it DFLEX exchange. And Christian's going to talk about it right after my talk. So we hope that the future will be driven by demand. Now, can we rely on utilities? Maybe not. I mean, they have an invested interest in containing the wires and so on. So that might not be where the solution will come from directly, maybe. There could be some surprises. Actually, the Koreans, the KEPCO, which is the Korean national grid company, they actually are talking to Samsung and LG about having a national DC grid, which is actually supported by the Korean government. And Singapore is doing the same thing. And if Singapore is doing, I'm sure China's doing it as well. So, there might be some surprises, and things can happen faster than we think. But the great demand for DC will be from the data centers. Hopefully, there will be some DC microgrids. Electric vehicles are still going strong in other parts of the world, renewable resources, telecommunication infrastructure, and also the robotics in industrial automation. Now, I can't talk about all of that. I mean, there's some good reports you can read, which will kind of cover that. But I want to focus on DC microgrid and creation of the local networks. So what's the sort of the basic unit of a microgrid? It's actually called nanogrid, which would be a microgrid on a single unit. And that would be a typical, say, building with renewables on the roof, which would have the energy storage and would supply the local loads to cars, computers, you name it. Now, that can be either off-grid, islanded, or it can be connected to the grid. And if you have a number of these different buildings, and they might have the renewables already on the roof, or they might not, if they create a community, then they can have some of these resources, coming from outside as well. So probably the best nanogrid house is this building in Purdue University, where they took a very standard 200 square meters house. They didn't do actually anything to it, not much of a conservation, but they installed the microgrid, and they've been now monitoring it for about 9 years. And that has the typical the solar, the batteries, and all the loads, and it's also connected to the grid. They actually they'll be publishing either this year or early next year the kind of a big report on that. So I'm really curious. I'm really looking forward to what that report's going to say, particularly what's going to be the kind of a comparison with ordinary house, which will be really interesting. I have been actually a guinea pig for the Panasonic solar and energy storage system in Muskoka, and I certainly don't regret it for a minute. We have lots of outages in Muskoka, and so having that kind of a resiliency and that kind of a backup is just fantastic. And we don't have a kind of a full house. We just have the essential loads, which are the fridge, the water pump, the sewage, the main lighting, and the plugs. So I can keep on working when the power's out. But as I say, it's really tremendous to have something like that, particularly in areas which are prone to outages. So there are tremendous benefits to that kind of a sort of things. If you have most of the loads behind the meter, then the transformer can be a lot smaller. So it is a great advantage to the utility. For the user, if you can actually charge your battery at night at lower rate, again, it's a great thing for your pocket. It's you're saving lots of money. But again, I would think the main advantage is the uninterruptible power, that you have that kind of a resiliency, and it keeps going. Now, DC compatible devices. Now we already have DC lighting. It's pretty common. Most of the appliances can run on DC. Yes, there is a premium. But the premium, it's not a technical issue. It's an ecosystem issue. There's no market. That's what it is. And in fact, the dirty secret is that some appliances actually do run on DC, but you have to convert it from AC to DC. So it really is a question of the market. It's not a technical issue. And there are some innovation. For example, Tridel already have this innovation suite at the well, and they do have the DC lighting. They do have the fan coil, smart thermostat, radiant floor heating. They're actually producing some power from their balconies. They have these kind of a see-through glass panels on the balcony, so they're generating some of that power, which then is controlled by the DC microgrid. And they have these kind of combined outlets. So you have the DC and the AC outlets throughout the whole suite. In Europe and in Asia, there's more and more these kind of a smart, integrated, decentralized energy systems, which look very comprehensively how those kind of systems are being integrated in building or in communities. And I mean, the great thing about Europe is they have this consortia. It's a number of companies collaborating with each other, which we don't do very much. We don't have that kind of a purchasing system established here. And you have some pretty heavy hitters like Fraunhofer Institute, which is kind of the equivalent of the MIT in Europe. So these things are moving pretty fast, and they're going to be very interesting. Now, there is a number of these microgrids already in existence, and particularly in type of buildings which do need uninterrupted power. So hospitals would be one example. Certainly, Kaiser Permanente has been one of the pioneers in putting this DC system in their hospitals. In Canada, actually, the First Nations are the greatest pioneers of this kind of a sort of things. I guess they have the same problem as I have in Muskoka. There's a number of these different microgrids in the First Nations now. Data centers. Now, the data centers do need the uninterrupted power. They need a lot of it. But there's also another aspect of it, which is the space aspect. They really need the space for the power racks. And if you have all these UPS, which are, run AC, they take lots of space. And if you have these large AI data centers, they really are, the spaces and premium. So more and more data centers are going for DC, Google, and Jim was referring to the demand. Eric Schmidt was just kind of saying at that hearing in a Congress. And they everywhere, China and so on. So then we have campuses, which also have lots of DC microgrids, and there's a number of examples. Here in Canada, we actually have an example in Burlington, which was done by a local company called Arda in 2018-20. And it's a building which does have the solar, does have the battery storage, EV chargers, and the lighting. But all the things the utility sees is just this 15 kilowatt power. Everything is behind the meter. So I'm sure it's a great advantage to the building. There are also commercial and industrial microgrid. Companies which have lots of robotics like Tesla or Honda, the car companies, they have installed DC microgrids. IKEA and other retailers are having these microgrids, and also some operation which are 24 hours, like transportation facilities like port, airports. Schiphol, for example, in Amsterdam, runs on DC. Now, another kind of interesting thing is the power over internet, which is a DC thing. And Cisco has been pioneering this kind of a system. In fact, most of the Cisco installed workspaces do have this power over internet. And so that's kind of being used around. Sinclair Hotel in Fort Worth is a poster child for this kind of buildings. And that's been very interesting. It was also Cisco installation, but this is where you start merging energy and communication system. And companies like Cisco and are now starting to work with energy companies trying to merge that. And what's kind of really interesting is what's the future will be then in digital grid, which will be the internet of energy, which will then create a two-way software coordinated, data-driven, intelligent layer on the top of the physical system. And the hope is that the internet of energy will provide the same thing as the actual internet did for the communication. That is connecting these different devices. So the energy actually flows reliably, efficiently, securely, and saves the money as well. So how does this work? I mean, essentially, you overlay the data over the energy network, and there are 4 different levels. The devices needs address. The devices has to be readable and measurable. And here in Ontario, we have a great advantage because we have the green button. So, we already have those kind of data. And the devices have to speak the same language. And there's got to be transaction element. There's got to be a marketplace. And again, I think Christian's going to talk about that. So, in conclusion, this is what the market leaders say. Go directly DC for the new energy tech. EV, solar batteries, data centers, they all DCs, and transition to DC distribution. I mean, that's what's happening around the world now, in Asia, in Europe. And if we're not going to do it, we're going to be left behind. So go for it. I've actually wrote this paper for the LG Nova called Coalition for Innovation. It's called Futures Direct. So if anybody wants the reference to it, I'll be happy to give it to you. Thank you very much.